Let's first prove the upper bound, that T of n is in big O of n to the power log base b of a times log to the power k plus 1 of n. Here's the expression for T of n again. T of n is n to the power log base b of a times T of 1. This is the cost associated with the leaf nodes of the recursion tree. And this summation from I equal to 0 to h minus 1 of a to the power I times f of n divided by b to the power I is the cost associated with the non-leaf nodes. This term in particular is the level sum at level I, and we are summing together the costs or the level sums from level 0 to level h minus 1. And this is the this is the level sum for level h, or the cost associated with level h. Now what we are given is that f of n is sandwiched between two constant multiples of this function. So we are going to focus only on this inequality, the second inequality among the two, because that's what is going to help us prove the upper bound. So let's just focus on the second inequality, which is that there exists a constant C2 which is positive such that f of n is bounded from above by that constant multiple of n to the power log base b of a multiplied by log to the power k of n. Now our strategy is going to be to replace this term f of n divided by b to the power I by something larger than it, and we are going to use this inequality to derive some function that is larger than f of n divided by b to the power I. So if we substitute n divided by b to the power I in place of n everywhere in this inequality, this is what we'll get. F of n divided by b to the power I is less than or equal to C2 times n divided by b to the power I, the whole thing raised to the power log base b of a, multiplied by log to the power k of n divided by b to the power I. So we get this inequality by just a simple substitution of n to the power b, n divided by b to the power I for n. Now given this, we could take this term and replace it with the right hand side of this inequality. Okay, so imagine taking this and replacing f of n by b to the power I, which is the LHS here, by the RHS. As a result of this substitution, we will be increasing the value of this summation because we are substituting this term by something larger than it. So if the value of the right hand side goes up, then T of n will be less than or equal to the resulting right hand side, because T of n is equal to this. So if we increase this, T of n will become less than or equal to the resulting expression. So the resulting expression will be T of n is less than or equal to, the first part remains the same, n to the power log base b of a times T of 1, and in the second part we are taking this RHS and plugging it in place of f of n by b to the power I. Now if we just focus on this second expression, we can simplify it by pulling C2 outside the summation and also pulling n to the power log base b of a outside the summation, because both these terms are independent of I. They don't depend on I. So we can pull them out of the summation. And what will be left inside the summation? This a to the power I will remain as it is. These two terms have been pulled out, but we'll have a b to the power I, the whole thing raised to the power log base b of a in the denominator. And this term will remain as it is. Now let's look at this term, b to the power I, the whole thing raised to the power log base b of a. We have seen in earlier videos when we discussed the proofs of different cases of Master Theorem that we had this common step of exchanging powers, exchange by swapping the order of powers. So if you have a to the power I raised to the power j, you can reorder the powers as a to the power j and then the whole thing raised to the power I. We'll do the same thing here. We'll first take b to the power log base b of a and then raise the result to the power I. And why do we want to do this? Because b to the power log base b will cancel each other out, and this is basically a. So this will be a to the power I. So if this is a to the power I, there is an a to the power I in the numerator, and both these terms will cancel each other out. Now, if you remember, we are trying to prove that t of n is bounded from above by some constant multiple of n to the power log base b of a times log to the power k plus 1 of n. You will need to keep in mind the final form of the inequality that we need to prove to understand why we are to understand the kind of transformations that we'll be doing now to get a constant multiple of n to the power log base b of a times this function on the right hand side. And we need to prove that t of n is less than or equal to some constant multiple of n to the power log base b of a times log to the power k plus 1 of n. So how do we get it on the right hand side? Well, if we want log to the power k plus 1 of n on the right hand side, one way to do that is to replace this log to the power k of n divided by b to the power I by log to the power k of n, because we ultimately want log to the power k plus 1 of n as the multiplier associated with n to the power log base b of a. So note that we are looking at the second term only here. We already have a constant multiple of n to the power log base b of a, and these two terms have already cancelled each other out. So we are basically left with this summation from I equal to 0 to h minus 1 of log to the power k of n divided by b to the power I. And we want this summation to be either equal to or be less than or equal to log to the power k plus 1 of n. So that if we replace this whole thing by log to the power k plus 1 of n, t of n will turn out to be less than or equal to, of course, this first expression plus some constant multiple of n to the power log base b of a times log to the power k plus 1 of n. So if we replace n to the power n divided by b to the power I by n everywhere, there are basically h terms in this series. The first term is log to the power k of n. Second term is log to the power k of n by b. The third term is log to the power k of n by b square. And we are adding all these terms. Up to I equal to h minus 1. What I'm saying is these arguments n by b square, n by b to the power h minus 1, throughout this summation, all these values are less than n because b is greater than 1. So n by b must be less than n by b square must be less than n, and so on. So if we replace each of these by n, if we replace each of these by n, we will be increasing the value of this summation. So what we will do is, we will replace n by b to the power I by n. And if we do that, we'll be getting something larger because this number in general is less than n. It's some fraction of n. So by replacing a fraction of n with n, we'll be getting something larger. And we're also using the fact that log of n uh, is a monotonically increasing function of n. This means if we have two values a and b such that a is less than b, then log of a will also be less than log of b. So if we are replacing the argument of the log by something larger, then the value of the log will also be larger. So the advantage of doing this is that this function log to the power k of n is independent of I. So it can again be pulled out of this summation. And what will be left in the summation? Well, nothing, just 1. So the summation will then be sigma of I equal to 0 to h minus 1 of 1. So after substituting n by b to the power I by n, this is what we got. And then we could pull this out of the summation and we'll be left with a 1 inside. And because there are h terms, this will not be equal to h. This is equal to h. Or equivalently, we could have said that since log to the power k of n is being added to itself h times, this summation evaluates to log to the power k of n multiplied by h, right? Which is what we'll get here, log to the power k of n multiplied by h. Now what is h in terms of n? H is log n to the base b, right? H is the height of the recursion tree, which is log n to the base b. We have seen this earlier, so I'm just reusing that fact. So if we replace h by log n to the base b, which is the value of h, we will be adding one more power to log of n, and we'll get log to the power k plus 1 of n. And this is what we wanted. because we need to show that t of n is bounded from above by some constant multiple of this function. Now we do have this term, but this is a lower order term because this is n to the power log base b of a, and this is n to the power log base b of a multiplied by another function of n. So this is a lower order term, and we can in fact easily prove that this whole sum is less than or equal to c2 plus 1 times n to the power log base b of a times log to the power k plus 1 of n. Basically what I'm doing here is I'm saying that because this is a lower order term, we can take the coefficient of the dominant term, add 1 to it, and claim that the dominant term with this extra 1 in the coefficient is going to be greater than or equal to this left hand side. Right, this was a standard technique that we used earlier in the videos on asymptotic complexity to prove that some function is in big O or big or theta of n, theta of some function f of n. So that's what we are doing here. We can claim that this whole expression is less than or equal to some constant multiple of n to the power log base b of a times log to the power k plus 1 of n. Because this is what we need to show in order to claim that t of n is in big O of this function. We need to show that this entire right hand side is less than or equal to or bounded from above by some constant multiple of this function. And we are choosing the constant to be one more than the coefficient of the dominant term, because that will allow us to make this claim more easily, because this is easy to prove. If you take this term to the right hand side, the functions are the same, the coefficients are different. So if you take this term on the right hand side, the coefficient will become c2 plus 1 minus c2. So we will be left with just 1 multiplied by n to the power log base b of a times log to the power k plus 1 of n. And this n to the power log base b of a will then cancel out with this, and we'll need to show that log to the power k plus 1 of n is greater than or equal to t of 1, which is obviously true for large n. So this claim is clearly true for large n. So t of n can be claimed to be bounded from above by some constant multiple of n to the power log base b of a times log to the power k plus 1 of n. This means that t of n is in big O of n to the power log base b of a times log to the power k plus 1 of n. So we have proved the upper bound. We wanted to prove that t of n is in big O of this function, and we've proved that. We've shown that t of n is bounded from above by a constant multiple of this function. Now, I hope you see the overall strategy we used. We used the given information that f of n is in theta of this function, which is what is given to us in this extended version of case 2. We then use the definition of theta notation to claim that f of n is sandwiched between two constant multiples of this function. And then we focused on this inequality. And why did we focus on this inequality? Because if f of n is bounded from above by this function, then we can take the expression for t of n and replace the occurrence of f of n by b to the power I by the corresponding upper bound on f of n by b to the power I, which is derivable from what is given to us. And then we take the right hand side or the upper bound on f of n by b to the power I and replace it and replace f of n by b to the power I by its upper bound. And as a result, this whole expression becomes an upper bound on t of n. And then we simplify this expression to end up with just sigma of I equal to 0 to h minus 1 of log to the power k of n by b to the power I. This is of course the simplification of just the second term here. The first term ends up being irrelevant because it turns out to be a lower order term. But just focusing on the second term, we then further replace this n by b to the power I by just n, thereby making this whole expression even larger. And then that allowed us to pull out log to the power k of n from the summation, leaving nothing inside the summation. So the summation then trivially evaluated to h, which was nothing but log of n to the base b. And this log term contributed to the extra power to log of to log n raised to the power k. So we got a power of k plus 1 for log n. And we could then justifiably drop the lower order term by arguing that since this is the higher order term, this entire expression is bounded from above by some constant multiple of this higher order term. And the constant that we chose to prove this was just one more than this coefficient here. And thereby we were able to show that t of n is bounded from above by a constant multiple of this function. And so t of n is in big O of this function. In the next video, we will prove the lower bound on t of n. That is, we'll prove that t of n is also in big omega of this function.